All right, hello and welcome to Berg CS, and we are going to be covering Module 1 of Assembly and Computer Organization. Today we are going to be talking about digital signals and systems. Now, I like to start this off by just asking the general question, why do we teach programmers computer organization? Now, there are a couple of simple answers. Understanding the low level operations and the logic that makes computers work, um, essentially, the way computers think, act, perform tasks, will make you a better programmer. It'll make you better able to communicate and develop logical structures that the computer is able to recognize. Um, it will allow you to create more performant applications and understand where those lines are. Now, another thing is that, generally speaking, the way we design and structure systems is the same from the bottom up. The way that we handle storing, transferring, and processing data within memory, these structures are replicated at the higher levels. Certainly at the higher levels, they are abstracted away from to a certain degree, but the general structure is there. So we are looking deep inside of these systems to get a better understanding of how they work, and that will allow us to do more meaningful work at the higher level. Now, one thing I would like to note is that embedded engineers, they make good money. They're always in demand. That demand is always growing. There are tons of programmers out there that can build web applications. There are fewer, much fewer programmers out there that are able to write code for embedded systems. This is stuff that, makes an elevator get off at the stop that you push the button for. This is the technology that, runs inside of most modern motor vehicles. And being able to work on this stuff, industrial equipment, while it isn't as flashy as we tend to think of application development as being, it's rich work, rewarding work, and it is rewarding professionally and financially. So it's a very good field to go into, and I like to point that out because it's very common to come into programming and start looking at things and being like, oh, I want to make apps, or I want to build websites, and we don't really think about the lower level tasks that require, the same amount of knowledge, expertise, and we kind of just we stop at that higher level and we don't keep going very often. Now, today we are going to be talking about signals. Particularly, we're going to be talking about, oop, there goes my cursor. We are going to be talking about two types of signals. All right. So the first one we're going to discuss are non-digital signals. Now, non-digital signals is a term used in opposition to digital signals, which we'll talk about next. But non-digital signals are probably more commonly known as analog signals. Now, analog signals are not discrete values. Discrete values are things that we can count. They are continuous values. Basically, the closer you get to the value, the more accurate you get. And when we talk about accuracy with these, I gotta figure out where my hand is. When we talk about accuracy with these systems, what we are talking about is we've got a floating point number. So that's a number that's got a decimal point. And accuracy is how many digits we represent after that decimal point. Now, with analog values, that accuracy, also known as resolution, is infinite. So these numbers carry on forever and ever and ever, which means that these values move along this spectrum, and at any point, no matter how small you want to get, you are going to get a slightly different value from one increment to the next increment. So this part of the little hump is different from this one, different from this one, and no matter how small you get, you're still going to see those differences occurring. These are continuous values. I'm not scoped properly here. All right. So analog signals we will contrast with digital signals. Now these are signals that are designed to be read, interpreted, and processed by computers. Now computers have a couple of problems when it comes to representing analog values. And these problems stem from the fact that we have a fixed amount of resources. So we have a fixed amount of storage in our computer, a common size for, let's say a hard drive. And we'll talk about what these measurements mean later on. But, let's say we have a 1 terabyte hard drive. Now, 1 terabyte, that is a discrete value. That means that we cannot exceed the storage capacity of this device. So that becomes a problem when we want to represent a value that is infinite. We cannot store infinite values in finite spaces. So it's important to note that when it comes to resolution, and once again, resolution is how many numbers we get after that decimal point. That is fixed in a digital system. When that signal is converted to digital from analog, we have to pick a point at which to stop representing that number. We have to round, mathematically speaking, at a certain point. We can't just keep going on and on forever. Now, when we want to convert an analog value, a continuous value, what we do is we take little snapshots of discrete values along that signal at various points. Now, those little snapshots that we capture are referred to as samples. So right here, we're capturing the value at this position, and for the sake of what we're doing right now, we'll call that value 1. Now in this position, we'll call that value 0, and in this position, we'll call that value 1 again. We'll say that these two are the same or close enough to being the same to capture them both as 1. Now, the speed or the frequency at which we do the sampling is referred to as the sample rate. So let's assume that somewhere around here we have a theoretical value that is somewhere around 0.5. Now, when we capture that information digitally, it's going to look quite a bit like this. So we will be at 1 here, we'll be at 0 here, and we'll be back at 1 here. Now, if you'll notice, we transition immediately between 1, 0, and 1. So the times where this value is anywhere between 1 and 0, or 0 and 1, all of that information is lost. So one of the solutions for this is to increase our sample rate. So let's say we sample twice as frequently, and all of a sudden, we are capturing those half values. Now, that's fine, but you can go as far as you want with this. Because as we said, this analog signal, these are continuous values, which is to say there are an infinite amount of values between that 0.5 and that 0. Anywhere on that line, we could take a sample and we would end up with a different value. So there is a trade-off when it comes to capturing samples. Because if we sample too often, we might get a more accurate data set, but we can run into other problems with processing power, data, storage. Now, one way to lose data is to lose data in between samples. Now, another way to lose data is to say, let's round. So using standard mathematical rounding, we would turn this value, if we wanted to round it to the 10th, we would turn this value into 1.3. Now the problem with this 1.3 here is, depending on the accuracy that you require in what you're measuring, this number, 1.3, is a very different number than 1.25, etc. And when it comes to things that require intense amounts of precision, that isn't acceptable. So the more precision we require, the further along we will round. But no matter how far we go down this line, if we go 100 places down the line, 1,000 places down the line, if we go 1,000,000 places down the line, we will be increasing our accuracy, but we will never be as accurate as the analog value. There will always be data lost. So we have to have a tolerance for loss between how we do our rounding and between the frequency at which we capture our samples. So there is always loss. And a little thought experiment I like to do with this is, when we think about analog values, we'll think about things like digital clocks, or not digital clocks, analog clocks, thermometers, stuff like that. But basically anything in the natural world that exists that we measure will have an analog value. So I have a weight. That weight is analog. If I shift one atom in either direction, my weight will change at the atomic level. So it's continuous. These things are always continuous. They're constantly in flux. Which brings us to the concept of teleportation. So for this thought experiment, we will make a couple of assumptions. The first one being that teleportation is solved. We know how to do it. We can mechanically perform the task. The second assumption that will be that, just like in Willy Wonka, the way we do teleportation is we break you up into a bunch of little pieces, reassemble them down at the end. Now, we would be using technology that is ancestor to our current computing technology, which means when we capture this data of who I am as a person, we have to convert it to digital. I am analog, but if you want to transport me through a computer, you need to do it digitally, which means we are going to have a question of sampling, and we are going to have a question of rounding, which is to say that if I am digitally transported from one place to another, what I come out how I come out on the other side is going to be fundamentally different than who I was when my data, the data that comprises me, the analog information, when that was converted to digital. Some of that is going to be lost. Some of who I am as a person is going to be lost. And depending on how dramatic or silly you want to get with, some of the rounding or some of the sampling, you could potentially create a situation where I start on one end of the transportation as a person, and I end on the other side as a pile of spaghetti. Ideally, that's not what we want to do, but it is definitely, it is a slightly less philosophical version of the old argument, or the old thought experiment. If you're broken down and transported from one place to another, does that version of you die and then another version of you be born? I think that was taken from Star Trek. I don't watch it. But effectively, when we talk about how these computing systems work, when we talk about how these signals work, how we transfer this data, it's true. You are fundamentally a different person than when you started. You're different. You're changed. And there's no way to get around that because we do not currently have a way to digitally represent the infinite values that make up an analog signal. Now, when we talk about the conversion process, so typically speaking, you will have some hardware and some software running in conjunction. So to begin with, you will have a sensor. This is something that can capture analog data that's out there in the world. So this could be, and to bring it really close to home, the microphone that I'm speaking into, the webcam that is capturing my desktop. These things are capturing analog values in the real world. Now, when those are captured, they go through a process called signal conditioning. Now, you might ask, what is signal conditioning? Why do we need to do it? And I'm going to ask, where did I put my pen? Gotta be kidding me. I cannot trust myself with anything. My black pen was sitting on my black keyboard, so that is super helpful. Okay. So, when we take in an analog signal, this was my example a minute ago of an analog signal. However, analog signals exist in the world. There is interference, there's noise, there's all kinds of stuff that happens to an analog signal before it hits a sensor. So, to more accurately represent a stream of analog data, it would probably look quite a bit more like this. Now, the problem with this is the noise. You capture a value here, it's going to be dramatically different from the value here, even though what is effectively happening is we have a curve. We don't have a curve represented in space because of the noise. So one of the first things that we do is we do something called signal conditioning. And we have developed over the years and continue to develop algorithms that discern the noise from the data that we actually want to send. And we just smooth that out a bit so that we have a cleaner source for sampling. Now, the last tool that we'll use, it's usually a piece of hardware that will sit inside of your capturing software, or you're capturing hardware, or it will be something that is on the other side of the board, but it is effectively an interface. in between your conditioned signal and the hardware and operating system that has to decide what to do with your signal. Now, what we do is we will take these values. So let's give this a slightly more descriptive value. I don't want it to be 0 and 1 here to confuse you, but effectively when we capture this, we will convert these numbers to a numbering system called binary, which we will talk about here in a few slides. So that looks like 10. Very important to note that that is not 10, but we'll talk about that more in a second. But the analog to digital conversion process is effectively turning this signal and the samples that we captured in that signal into ones and zeros, data referred to in this sphere as bits. Now, here's the thing about these bits is we have this as a representation of our signal. So let's put this all together and make it one big number. Now, you don't have to know exactly what that means right now. But when we transfer this, we can transfer it just as numbers. So when we look at this here, when we look at our analog signal, there are devices, and have historically been devices, that will send out these analog signals. And we have sent these analog signals out, really honestly, over great distances. Now, the most common example for this is sending out these signals electrically over the copper cabling that comprises the telephone system. Now, there's two things that happen to these signals when they travel over this copper cabling. The first one is referred to as attenuation. Now, attenuation is the loss of a signal over distance. All right, so if we have to travel, let's say 1 mile, over the course of that mile, with no external interference, we will see a degradation over time of our signal. Now, we got over that, particularly with the telephone thing, or with the telephone issue, by using signal boosters and repeaters. And what they would do is at a certain point, they would intercept the signal and just crank up the volume on it a little bit. Now, the problem is when you increase the volume of the signal, when you increase that resolution of the signal, when you pump that up, you also pump up the noise that's been attached. So over this process, noise will continue to attach itself as we repeat this signal. So the noise is going to get louder and louder, and there's going to be more of it. And that is why early long-distance phone calls, analog long-distance phone calls, it was very difficult to understand the person on the other end of the line. The reason for this is because we were just blasting out this signal and cranking up the volume on it anytime we hit a point where it was degrading. And that amplified the noise. Amplify, that's the word I was looking for. Not pumping up the volume. Don't listen to that. But we amplify both the signal and the noise attached to the signal. So we would get to a point where the signal was more noise than signal, and what was originally intended, what was originally meant to be set. Now, the beauty of turning the signal into ones and zeros is though that string of ones and zeros is going to be the same string of ones and zeros no matter where you send it, no matter how far you send it. This doesn't change. Now, that is one benefit to converting analog data to digital. Another benefit is that we can apply something that we call post-processing. So post-processing, and let's look at the field of audio and music. Traditionally, before everything started to go digital, we would have specialty hardware where if you wanted to perform post processing to change the nature of the sound that you were getting, you would run it through these specialty devices, and usually you would have a bunch of them. You would have one for every task you would want to perform. Now, the thing is with digital is we have developed algorithms that look for patterns and will perform changes to this string of data that mimic the effects of these post-processing effects. Now, another thing we can do is we can compress this. So we can create algorithms, which is effectively, in this circumstance, we're going to describe it as a set of rules or a set of steps that we perform on a data set to achieve a result. So let's say, we wanted to compress this. Now we could set up a set of rules that say, for every 2 blocks of data, if we get a repeating set of numbers, we could just crunch them together. Now there for every 2 blocks there actually aren't any repeating, so we'll create an example where there are. So if we established this rule, we could take these 6 bits and we can crunch them down, and we will have something on the other side that knows how to interpret this and can say, okay, these are duplicated blocks. But while we have these here, we are able to represent functionally the same amount of data in less space. Now, the process of turning this into this is typically referred to as encoding. The process of turning this back to this is typically referred to as decoding. So if we think about MP3s will take digital sound information, and it'll use a proprietary algorithm to make that number smaller in storage. So effectively, we encode the file as an MP3. And then historically, MP3 players did this. Just about every hardware, software, music player nowadays will have something on board to decode an MP3. But effectively, an MP3, while it is sitting in storage, that is to say, while it's not being recorded and it's not being played, it is significantly smaller than it would be if it was just recorded raw, or if it was encoded using a different format. So that is one of the ways we are able to use binary data, digital signals, to improve the way we store, the way we transfer things by making them smaller, making them more manageable. Now, on to the representation, and we're going to get a little bit deeper right here into binary. Now, we store data, we represent data, we think about data within computing as being a collection of bits. And a bit can have the value 0 or it can have the value 1. Now, the reason we do this is because of a component called a transistor. Now, transistors are the primary logical units that make modern computing possible. And essentially, a transistor will exist in two states. The first state, which we will, for the purpose of getting through these next exercises, we will call this first state logic 0. At logic 0, electricity cannot flow through a transistor. Now, when electricity can flow through a transistor, we refer to that state as logic 1. But you can think of this as anything. It could be any two opposing values. It could be on or off, like a light switch. But for our purposes, we're going to abstract away from that a little bit and just think of this in terms of logic. So we have a logical 0 and a logical 1. All right. Let me move this over just slightly so that we can see all of this. And then let's go ahead and get a new page rolling. Okay. I gotta get a better setup for this stuff. But for the time being. So when we talk about digital signals, you got to see this bad boy for a second. And we're going to spend some time with it because this is the fundamental way that we describe digital signals. Now, this shape right here, this structure, is referred to as a pulse train. And if you can guess, it looks, it looks a little bit like a train. But effectively, it also runs like a train. We operate, with values that move up and down on one axis that is moving constantly across a second axis. Now, and we're going to talk about these axes real quick before we move on to some more definitions. But we have the y-axis up here, and for some reason whenever I do this my y's look like x's, which isn't super helpful. Now this y-axis will represent at this point logic 0 and at this point logic 1. Now this x-axis here actually represents time. And it is very important to note that these things are occurring over time. So digital signals are discrete values that are represented across a period of time. So we've got our pulse trains here, and I'm going to make us a little room by doing us a second little diagram. But we can break this pulse train up further. Now, of the components within this pulse train, one of the first ones to talk about is edges. So this edge here that you see moving up in this direction, now this is moving from logic 0 to logic 1. And in fact, an edge is actually defined as the transition either between logic 0 and logic 1, or the transition between logic 1 and logic 0. So when we move from logic 0 to logic 1, we get ourselves a rising edge. And this is simply, as you can see, because this edge is working its way up. Now on the other side, an edge that is moving between logic 1 and logic 0, we're going to call that a falling edge. All right, and I usually do this with a whiteboard. Got a lot more room on the whiteboard. Now, we're going to make ourselves another little diagram here, and we're going to talk about pulses. Now, an edge is a transition from one state to the other. A pulse is a transition from one state to another and back. So if we look here, and essentially we could also think of this as a sequential pair of rising and falling edges, or falling and rising edges. But each of these pairs is a pulse. So this guy right here is a pulse. This guy right here is a pulse. Now, just like we describe edges by the direction that they're going in, we describe these pulses by the direction they go in. So right here we're at logic 0, logic 1. If we move from logic 0 to logic 1, and then from logic 1 back to logic 0, that is referred to as a positive going pulse. All right, now conversely, if we start here as positive in logic 1, we move down to logic 0, and then back up to logic 1, we will call that a negative going pulse. Now this is a temporary transition. All right, a pulse is characterized by the fact that it moves to the next state and then it moves back. If it doesn't ever move back for any reason, we're not going to describe it as a pulse. Now, the next way we're going to describe pulse trains is by their shape. And we have two general shapes of pulse trains. Now, the first shape is the non-periodic pulse train. The non-periodic pulse train is characterized by the fact that there is no discernible pattern in the pulses occurring within the train. Now, you'll see this stuff when you send information over Ethernets. If you think about music, kind of going up and down, we see, and music, actually, now that I think about it, it is almost a terrible example, because it completely disregards rhythm, which will have a consistent pattern. I'll have to remove that from the slide, but well, it's too late now. And as we all know, you cannot edit video. Once you record it, it is there forever, or at least that's how I'm approaching things, because I'm not re-recording these. They take forever to record. All right, so those are non-periodic pulse trains. And we will go ahead and look at the converse. And, oh man, I had to put that on the other side, didn't I? Well, now this is okay. Here's what I'm going to do. I'm going to flip it. Oh, no, that is absolutely unreadable. Okay. I'll just stick to this side of the paper for this part. All right. Now, we have non-periodic pulse trains, but we also have periodic pulse trains. Now, a periodic pulse train is going to have a clear pattern. Now, these are very useful for things where timing is important. So, when we think about computers, an application of this would be the CPU system clock. We would use this clock to synchronize tasks. Um, in a car, one of the things that onboard computers are really good for is by timing the rate at which the spark plugs fire, and that has to be a consistent rate across the board. So we will use periodic pulse trains to represent a digital signal that has a consistent rhythm, a consistent beat. And we use these to synchronize events and processes. Now, we're going to talk about another definition that we use when describing these pulse trains. But one that we use, very important, is the period. So the period breaks down the identical parts of the waveform. So this right here, these two transitions, are mirrors of these two transitions. So each of these transitions would be a period. Now another way to write a period, a little shorthand for it, for the math people that like shorthands and symbols, we've got that uppercase T there. That uppercase T describes the period. Now within a period, the pulse, and it will, for our purposes, we will always describe this as the positive portion of the positive going pulse. But that positive going pulse, we will measure the width of it as the pulse width. And we have a shorthand for a pulse width, and that is lowercase t with the subscript W. If you can see that, I can barely see it. Now, the pulse width and the period will both be described in seconds or units of seconds. Now, when I say units of seconds, we could be talking about gigaseconds, nanoseconds, but we will always describe them as seconds. Now, something that you need to know about the pulse width is the pulse width always has to be greater than 0. Now, if the pulse width was not greater than 0, this would be our pulse train. which is not a pulse train. It would just be off. Now, it also has to be less than the period. Now, the reason for this is, and to illustrate this a little bit better, we will say logic 0 here for this. But if we were constantly at logic 1, this would be the shape of our pulse train. So there's no pulses in either one of these. So to have a pulse width, it needs to be greater than 0, and it needs to be less than the period. If it is the same as the period, then we are just always in logic 1. If it is 0, then we are always in logic 0. Really? Did I flipped it again? Okay. Let's get a new section of this paper to look at. Look at all that real estate. And in this market. Now, one of the measurements that we need to take for our periodic pulse trains is how often are these pulses occurring. Now, that how often is described as the frequency, which, if you ask me, is just the word for it. Now, frequency will be measured in the unit hertz. And we have, I think, in a slide or two, probably a couple slides, we've got a list of units. You can modify hertz one way or the other, but one example of the frequency of a periodic pulse train is for those of us that, build our computers or, have kind of done those, purchasing tasks or, shopped around for computers, laptops. One of the ways that we describe processors is by the frequency of that clock speed. It's one of the primary ways that we describe it. So you'll hear a very common measurement, or at least it was a few years ago. You'll hear it measured in gigahertz. And it's, I shouldn't have said a few years ago, because really honestly, we're nowhere close to the ceiling on gigahertz. We are not going up to terahertz yet. I don't know when or if we will. I'll probably eat these words because it's going to be on YouTube for long enough for me to be wrong. But, let's say you've got a clock speed, which is usually how they refer to it in advertising and stuff. You've got a 3.2 gigahertz processor. And you'll even say that sometimes. You'll even, when you're talking about your processor, you'll say, oh yeah, I got a 3.2 gigahertz processor. Another way we describe processors is by number of cores, but that will come later if it even gets touched on in this class. Multi-threading is a nightmare when you're first trying to figure out and wrap your head around how it works. It is insane. But for us to measure this frequency, we need to be able to calculate it. How did we get this 3.2 gigahertz? How did we get to that point? And we have a little formula for us here. So this is our frequency. And our frequency will be equal to 1, just the number 1, divided by the period in seconds, or that little t there. So we will take that period and we will divided into 1. Is that a proper way of saying that? We will divide 1 by the period. That is probably the more proper way of saying that. Now, like any good formula, if we already know the frequency, like we've got 3.2 gigahertz right here, we can actually flip that bad boy around and get the period, or t, by saying 1 divided by the frequency. Now, if this doesn't make a huge amount of sense, it will in the next video where I go over the lab for this, but for the time being, just look at those and know that we have a couple of formulas for figuring out our frequency or getting our period from our frequency. Now the next one. This one is, it can sometimes be hard to kind of wrap your head around this, but it is important to note, because we're just going to throw in another word here real quick. And as a matter of fact, I'm going to pull the Band-Aid off. Duty cycle. Duty cycle. So what are we talking about when we talk about duty cycle? Well, duty cycle isn't super specific in terms of expressions. And to be perfectly honest, I'd like to look into the etymology of that a little bit, because on the surface, it doesn't make perfect sense to me that duty cycle is the term we use to describe this. But the very important thing, and the simplest way to put this, is the duty cycle is the percentage of the time in a period we are in logic 1. Okay? So that duty cycle is the percentage of the time we are here within the period. So the period will be represented by these pulses, this identical segment, this positive going pulse, the percentage of the time we are here, that is our duty cycle. Now, duty cycle is always represented as a percentage. So, let's assume that our period here, and we'll make this a super easy number, but we will say that our period is 100 seconds. All right? And then we will say that our pulse width is 50 seconds. And remember, the period and the pulse width are both measured in seconds. All right? So the formula for figuring out this duty cycle is we take duty cycle and, oh man, you can't even see that. I hope that hasn't happened like half a dozen times during this video and just like you're screaming at your screen like, move it up a little bit. I can't see, just move it up a little bit. You can wait and yell at me in class. That's how we'll do that. Okay. So our duty cycle will be our period can't spell, that's our t, divided by, and I'm definitely not giving myself enough room for this, our pulse width, TW, and I'm absolutely not going to have enough room for that, so let's just start a new page. We'll start a new page for this. You guys are worth it. We'll do it. Okay. So, we'll go ahead and get some of our stuff back, but basically we have our pulse width here, our little TW, that is equal to 50 seconds. And we have our period here. This is equal to 100 seconds. And we will say that our duty cycle is equal to our period divided by our pulse width times 100%. Now that little times 100%, don't let that scare you. We use that just to turn it into a percentage. And oh man, hold on. I screwed it up. Let's try again. It has been a long week, and I got up early to record this for y'all because I keep telling you I was going to do it. All right. We divide our pulse width by our period and multiply that by 100 because it would be a very different number. So let's go ahead and plug our stuff in. So our duty cycle equals 50 divided by 100 times 100%. Okay? So bringing this down to the next step, that means our duty cycle is equal to 0.5 times 100%. And when we multiply 0.5 by 100%, which is to say, when we bring that decimal over, we end up with a duty cycle equal to 50%. All right, and the reason I did this as this example is because, as we can see here, and this I hope is the best way to illustrate this to you, this pulse right here within this period is 50% of the total size of the period, which is to say 50% of the time, that's our duty cycle, 50% of the time within the period we are in logic 1. Now, why does this matter? Why does duty cycle matter? One of the most common uses that we'll see, and you see it all over the place these days, is in LEDs. So an LED bulb can either be on or it can be off. All right? It is either putting out light or it isn't. Now the thing with that is, let's say we wanted to dim our lights. And as we know, a lot of us have dimmable LEDs. It's a super common thing to sell. But how do you dim something that can either only be on or off? It only exists in two states. Well, see, the LED light operates with a periodic pulse train. Now this bad boy, these LED lights, they flash so fast that our eyes can't perceive it, and our eyes kind of blur it together. Now the beauty of this is by decreasing that pulse width, and I'm not going to be able to do this super, assume that's equal. It is visibly, obviously not equal, assume it is equal. But by decreasing this pulse width, which decreases the duty cycle, we're actually able to dim that. The less often that bulb is on, or it's in logic 1, the less light we get hitting our eyes. So even though we can't perceive the individual flashes of on and off, we get less light overall. And that's what appears to make them dim. So an LED with a duty cycle of 20% will look quite a bit dimmer than an LED with a duty cycle of 80%. Now the duty cycle will always be a number between 0 and 100 inclusively. All right? And that is because we can be on 100% of the time, we can be off 100% of the time, and we can be values in between the two. But we cannot have a negative value, and we cannot have a value greater than 100%. All right? We cannot be on more than 100% of the time. We cannot be off less than 0% of the time. All right, and so we're going to finish with a little bit, and this will come up in the lab that we're doing next, but we have a handful of unit prefixes, and there's a little trick with these, but these are the unit prefixes that we will use in computing, any math that we do for computing, but they range, and these are common usage. They go a lot further up, a lot further down. Generally speaking, we do not typically need to describe numbers outside of these ranges, which is why we're not going to talk a lot about numbers outside of these ranges. But effectively, at the smallest, we have pico. At the largest, we have zeta. Or zeta. I think it's zeta. It's got 2 A's, right? But we also call it peta, and that has 1 A. Or 1 T. I don't know. I don't think it matters as much as what this little exponent here does. So for those of us that kind of sucked at math in school, the first time I ever saw this, I was like, okay, what does that mean? 10 to the 15th. What could that possibly mean? And effectively, it just means there are 15 extra zeros after the number that we are trying to describe. Now, on the other end, we've got 10 to the minus 9. Now, what does that mean? Well, all that means is you go in the other direction. So let's say we have 1 bit. Okay? Just 1. We got 1 bit. Now, if we wanted to describe 1 bit in kilobits, we would take this over and just move 3 spaces. Plug some extra zeros in there, and then all of a sudden that 1 bit is 0.001 kilobit. All right. Now let's say we go in the other direction. We've got that 1 bit, and we want to turn it into a millibit. So how many millibits is 1 bit? Well, we'll take this. We'll assume the decimal point is here, because in theory it is, and we'll just move 3 spaces over from that, or add 3 zeros, as you can see here. So 1 bit is 1,000 millibits. And that's more or less how that works. It gets a little bit tricky when you want to, let's say we wanted to see, okay, we've got 2 GB, and we will talk in a couple of sections about the difference between bits and bytes. We have 2 GB. We want to figure out how many megabytes that is. So we will take the difference between the giga and the mega. So that's 10 to the 9, 10 to the 6. And I don't know if you can see that up there, but take the difference of 10 to the 9 and 10 to the 6. That's going to give us 10 to the 3. So to move from gigabytes down to kilobytes, we will just do 10 to the 3. So we'll add ourselves 3 little zeros. 2 gigabytes is 2,000 megabytes. Now, that is mathematically speaking. When it comes to the way we describe storage, the way we describe memory, stuff like that, those numbers are actually approximate. And, that it doesn't mean that, if you have 2 gigabytes, that doesn't mean you have exactly 2,000 megabytes. It might be, something within a certain margin of error there. And actually, one of the reasons for that is because no, we're going to wait until we get into binary to talk about that, because I don't want to melt your brains with that one. But basically, there is a reason that when it comes to actual processing, why what we would call a gigabyte wouldn't necessarily be 2,000 megabytes. And it has to do with the nature of the base to the binary system. And now I regret bringing it up at all, but as we have said before, you cannot edit video. So it's here forever. I said it. Now that is the last slide. Join me if you would like for the next video in the series, which will be going over the material for Lab 1 and running through those problems.